Hello everyone, and welcome to my channel. This is an educational channel. We take a look at some great theories of everything and do deep dives into them, show you how what their potential is, how you can use them in your own life, help you with your paradigm shifting, your awakening to 5D consciousness, your formation of a holistic worldview. And today is our 507th video on the reciprocal system of theory from Dewey B. Larson. Mr. Larson was an American engineer who lived in the 20th century, died in 1990. In 1959, he proposed his two fundamental postulates about how the universe operated, and was one of the few scientists who attempted to construct his universe out of not matter, not energy, but motion. And his universe of motion, also known as the reciprocal system, was articulated primarily in his first postulate. And then he went through a process of deduction to turn his postulates into a theoretical universe. What his universe would look like if his postulates were correct. And then he compares his theoretical universe with the measured empirical universe of the modern scientists. And he does that in several works, but including this one here that is called Basic Properties of Matter, which we'll be reading from chapter 19 on magnetostatics today. We started this chapter yesterday, and so you might want to go back and start fresh if that's your thing. Otherwise, you also could get a more thorough briefing on the reciprocal system from me. If you watch any of my first 474 videos on this topic, I go into the postulates and their implications in a little bit more depth, a lot more depth in those videos. At this point, I'm pretty much just assuming that you have some working knowledge of the reciprocal system, and we're going to try to just get into the text and turn some pages so that we can get through this book. I will give you the that first postulate. The universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so the universe is made out of motion. In particular, Larson is talking about a motion that he calls scalar motion. That is a motion that has a magnitude, but it has no specific direction, which you can envision using a balloon that you put dots on. And if you blow up the balloon, all the dots will be moving away from each other. And they won't be moving in any specific direction. Every dot will be moving away from every other dot. So every dot will basically be moving in every direction, outward. And then if you contract the balloon, they will all be moving toward each other. And again, not in any specific direction. That is a scalar motion. And then motion in Larson's system is the relationship between space and time. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. And the basic example you can use is speed. The runner is running at 10 miles per hour. 10 miles of space in 1 hour of time. Space over time is speed. And every other kind of scientific phenomena is also a different kind of form of motion. Matter is a form of motion. Energy is a form of motion. Pressure is a form of motion. Acceleration is a form of motion. Force is a form of motion. They all have their specific time-space signature. Time and space can have multiple exponents. So, for example, matter is time to the third power over space to the third power in Larson's system. Okay. Again, check out one of my first 474 videos if you want to go a little bit deeper into the reciprocal system derivation. And right now we're going to check in here with magnetostatics. Right now he was kind of talking about the different two magnetic poles. And we'll start here. These poles constitute scalar reference points, as defined in Chapter 12. The effective direction of the rotational vibration that constitutes the charge, located at the north pole, is outward from the north reference point, while the effective direction of the charge centered at the south pole is outward from the south reference point. The interaction of two magnetically charged atoms therefore follows the same pattern as the interaction of electric charges. He gives a figure here which is identical to the figure that he uses for electric charges, except that it substitutes poles for charges. Two north poles move outward from north reference points and therefore outward from each other. Two south poles similarly move outward from each other. But a north pole moving outward from a north reference point is moving toward a south pole that is moving outward from a south reference point. Thus, like poles repel and unlike poles attract. On this basis, when two magnetically charged atoms are brought into proximity, the north pole of one atom is drawn to the south pole of the other. The resulting structure is a linear combination of a north pole, a neutral combination of two poles, and a south pole. Addition of a third magnetically charged atom converts the south pole to a neutral combination, but leaves a new south pole at the new end of the structure. Further additions of the same kind can be made, limited only by thermal and other disruptive forces. A similar linear array of atoms with north and south poles at opposite ends can be produced by introducing atoms of magnetizable matter between the magnetically charged atoms of a two-atom combination. Separation of this structure at any point breaks a neutral combination and leaves north and south poles at the ends of each segment. Thus, no matter how finely magnetic material is divided, there are always north and south poles in every piece of the material. Because of the directional character of the magnetic forces, they are subject to shielding in the same manner as electric forces. The gravitational force, on the other hand, cannot be screened off or modified in any way. Many observers have regarded this as an indication that the gravitational force must be something of a fundamentally different nature. This impression has been reinforced by the difficulty that has been experienced in finding an appropriate place for gravitation in basic physical theory. The principal objective of the theorists currently working on the problem of constructing a unified theory or grand unified theory of physics is to find a place for gravitation in their theoretical structure. Development of the theory of the universe of motion now shows that gravitation, static electricity, and magnetostatics are phenomena of the same kind, differing only in the number of effective scalar dimensions. Because of the symmetry of space and time in this universe, every kind of force or every kind of motion has an oppositely directed counterpart. Gravitation is no exception. It takes place in time as well as in space, and is therefore subject to the same differentiation between positive and negative as that which we find in electric forces. But in the material sector of the universe, the net gravitational effect is always in space, That is, there is no effective negative gravitation, whereas in the cosmic sector, it is always in time. And since gravitation is three-dimensional, there cannot be any directional differentiation of the kind that we find in magnetism. Because of the lack of understanding of the true relation between electromagnetic and gravitational phenomena, conventional physical science has been unable to formulate a theory that would apply to both. The approach that has been taken to the problem is to assume that electricity is fundamental and to erect the structure of physical theory on this foundation, further assumptions being made along the way as required in order to bring the observations and measurements into line with the electrically based theory. Gravitation has thus been left with the status of an unexplained anomaly. This is wholly due to the manner in which the theories have been constructed, not to any peculiarity of gravitation. If the approach had been reversed, and physical theory had been constructed on the basis of the assumption that gravitation is fundamental, electricity and magnetism would have been the undigestible items. The kind of a unified theory that the investigators have been trying to construct can only be attained by a development such as the one reported in this work, that rests on a solid foundation of understanding in which each of these three basic phenomena has its proper place. Aside from the effects of the difference in number of scalar dimensions, the properties of rotational vibration that constitutes a magnetic charge are the same as those of the rotational vibration that constitutes an electric charge. Magnetic charges can therefore be induced in appropriate materials. These materials in which magnetic charges are induced behave in the same manner as permanent magnets. In fact, some of them become permanent magnets when charges are induced in them. However, only a relatively small number of elements are capable of being magnetized to a significant degree, that is, have the property known as ferromagnetism. The conventional theories of magnetism have no explanation of the restriction of magnetization in this sense to these elements. Indeed, these theories would seem to imply that it should be a general property of matter. On the basis of the assumptions previously mentioned, the electrons, which conventional theory regards as constituents of atoms, are miniature electromagnets and produce magnetic fields. In most cases, it is asserted, the magnetic fields of these atoms are randomly oriented, and there is no net magnetic resultant. However, there are a few elements in whose atoms the fields from the different electrons don't exactly cancel. And these atoms have a net magnetic field in a few materials. The magnetic fields of the atoms line up with each other. Now that is a quote. Doesn't really say where that's coming from. There's a footnote there. But, anyway, such materials, it is asserted, have magnetic properties. Just why these few elements should possess a property that most elements do not have is not specified. For an explanation in terms of the theory of the universe of motion, we need to consider the nature of the atomic motion. If a two-dimensional positive rotational vibration is added to the three-dimensional combination of motions that constitutes the atom, it modifies the magnitudes of those motions, and the product is not the same atom with a magnetic charge. It is an atom of a different kind. The results of such additions will be examined in Chapter 24. A magnetic charge, as a distinct entity, can exist only where an atom is so constituted that there is a portion of the atomic structure that can vibrate two-dimensionally, independently of the main body of the atom. The requirements are met so far as the magnetic rotation is concerned, where this rotation is asymmetric. That is, there are n displacement units in one of the two magnetic dimensions and n plus 1 in the other. On this basis, the symmetrical B groups of elements, which have magnetic rotations 1, 1, 2, 2, 3, 3, and 4, 4, are excluded. This has to do with Larson's notation for atoms. In Larson's system, just like everything else, an atom is a form of motion. In fact, an atom is a combination of motions. It is, so it has a 3-number, every atom has 3-number signature, and the first number is a 2-dimensional rotation. The second number is a secondary 2-dimensional rotation, and they alternate. And then the third number is a 1-dimensional rotation. And so those first 2 numbers are the ones he's referring to here, 1, 1, 2, 2, and 3, 3, and 4, 4. So those atoms where the 2-dimensional rotations are balanced, they are excluded from magnetic, ferromagnetic charges. While the magnetic charge has no third dimension, the electric rotation with which it is associated in the 3-dimensional motion of the atom must be independent of that associated with the remainder of the atom. The electric rotational displacement that must therefore exceed 7, so that one complete unit, 7 displacement units plus an initial unit level, so 8, can stay with the main body of the magnetic rotation, while the excess applies to the magnetic charge. Furthermore, the electric displacement must be positive, as the reference system cannot accommodate 2 different negative displacements, or motion in time, in the same atomic structure. The electronegative divisions 3 and 4 are thus totally excluded. The effect of all of these exclusions is to confine the magnetic charges to division 2 elements of group 3A and 4A. In group 3A, the first element capable of taking a magnetic charge in its normal state is iron. This number 1 portion is apparently favorable for magnetization, as iron is by far the most magnetic of the elements. But a theoretical explanation of this positional advantage is not yet available. The next 2 elements, cobalt and nickel, are also magnetic, as their electric displacement is normally positive. Under some special conditions, the displacements of chromium 6 and manganese 7 are increased to 8 and 9, respectively, by reorientation relative to a new 0 point, as explained in Chapter 18 of Volume 1. These elements are then also able to accept magnetic charges. According to the foregoing explanation of the atomic characteristics that are required in order to permit acquisition of magnetic charge, the only other magnetic, in this sense, elements are the members of Division 2 of Group 4A, magnetic displacements 4-3. This theoretical expectation is consistent with observation, but there are some as yet unexplained differences between the magnetic behavior of these elements and that of the group 3A elements. The magnetic strength is lower in the 4A group. Only one of the elements of this group, gadolinium, is magnetic at room temperature, and this element does not occupy the same position in the group as iron, as the most magnetic element of group 3A. However, samarium, which is in the iron position, does play an important part in many magnetic alloys. Gadolinium is 2 positions higher in the atomic series, which may indicate that it is subject to a modification similar to that applying to the lower 3A elements. Manganese, I think he was talking about, but oppositely directed. No, I guess that would be more like cobalt. Okay, if we give vanadium credit for some magnetic properties on the strength of its behavior in some alloys, all of the division 2 elements of both the 3A and 4A groups have a degree of magnetism under appropriate conditions. The larger number of magnetic elements in group 4A is a reflection of the larger size of this 32 element group, which puts 12 elements into division 2. There are a number of peculiarities in the relation of the magnetic properties of these 4A elements, the rare earths, to the positions of the elements in the atomic series that are as yet unexplained. They are probably related to the other still unexplained irregularities in the behavior of these elements that were noted in the discussions of other physical properties. The magnetic capabilities of the division 2 elements and alloys carry over into some compounds, but the simple compounds such as the binary chlorides, oxides, etc., tend to be non-magnetic, that is, incapable of accepting magnetic charges of the ferromagnetic type. In undertaking an examination of individual magnetic phenomena, our first concern will be to establish the correct dimensions of the quantities with which we will be working. This is an operation that we have had to carry out in every field that we have investigated, but it is doubly important in the case of magnetism because of the dimensional confusion that admittedly exists in this area. The principal reason for the confusion is the lack in conventional physical theory of any valid general framework to which the dimensional assignments of electric and magnetic quantities can be referred. The customary assignment of dimensions on the basis of an analysis into mass, length, and time components produces satisfactory results in the mechanical system of quantities. Indeed, all that is necessary to convert these mechanical MLT assignments to the correct space-time dimensions is to recognize the t to the third over s to the third dimensions of mass. But extending this MLT system to electric and magnetic quantities meets with serious difficulties. Malcolm McCaig makes the following comment, quote, "Very contradictory statements have been made about the dimensions of electrical quantities. While some writers state that it is impossible to express the dimensions of all electrical and magnetic quantities in terms of mass, length, and time, others, such as Jeans and Nicholson, do precisely that." End quote. The nature of the problem that the theorists face in attempting to arrive at an accurate and consistent set of MLT dimensions can be seen by comparing the dimensions that have been assigned to one of the basic electric quantities, electric current, with the correct space-time dimensions that we have identified in the preceding pages. Current, in MLT terms, is asserted to have the dimensions of M1 2Li 2T1. I guess 1 dimension of mass, 2 dimensions of length, and 2 dimensions of time. Not quite sure what that notation is. When converted to space-time dimensions, this expression becomes t to the third over s to the third times the quantity to the 1/2 times s to the 1/2 times 1-1 equals t to the 1/2 over s. The correct dimensions are s over t. The reason for this discrepancy is that the MLT dimensions are taken from the force equations and therefore reflect the errors in the conventional interpretation of those equations. The further error due to the lack of distinction between electric charge and electric quantity is added when the dimensions are assigned to the electric current, and the final result has no resemblance to the correct dimensions. The SI system and its immediate predecessors avoid a part of the problem by abandoning the effort to assign MLT dimensions to electric charge and taking charge as an additional basic quantity. But here, again, the distinction between charge and quantity is not recognized, leading to incorrect dimensions for electric current. These dimensions are stated as capital Q over T, the space-time equivalent of which is 1 over s, instead of the correct s over t. Both the MLT and MLTQ systems of dimensional assignment are thus wrong in almost every electric and magnetic application, and they serve no useful purpose. In our study of electrical fundamentals, we were able to establish the correct dimensions of the electrical quantities by using the mechanical dimensions as a base and taking advantage of the equivalence of mechanical and current phenomena. This approach is not feasible in application to magnetism, but we have a good alternative, as our theory indicates that there is a specific dimensional relation between the magnetic quantities and the corresponding electric quantities, the dimensions of which we have already established. The basic difference between electricity and magnetism is that electricity is one-dimensional, whereas magnetism is two-dimensional. However, the various permutations and combinations of units of motion that account for the differences between one physical entity and another are phenomena of only one scalar dimension, the dimension that is represented in the reference system. No more than this one dimension can be resolved into components by introduction of dimensions of space or time. It follows that addition of a second dimension of motion to an electrical quantity takes the form of a simple unit of inverse speed, t over s. The dimensions of the magnetic quantity corresponding to any given electric quantity are therefore t over s times the dimensions of the electric quantity. The dimensions thus derived for the principal magnetic quantities are shown in this table. So look at the table. We've got dipole moment t squared over s for he's separating out the magnetic and the electric quantities, but he's not always following his t over s rule. I don't think dipole moment he has his t squared over s, whereas dipole moment for magnetic is t over s. Charge t squared over s squared, flux t over s squared. Potential t squared over s to the third, vector potential t over s to the third. I guess he's saying that the factor there is just t. Flux density t squared over s to the fourth. Flux density for the would be t over s to the third. There the factor is t over s. Field intensity, oh, I think I see what's going on here. Okay. Okay, dipole moment is t. Dipole moment for magnetic is t squared over s. Charge is t over s. Flux for magnetic is T squared over S squared. Potential electrical is T over S squared. Vector potential for magnetism is T squared over S to the third. Flux density for electricity is T over S to the third. For magnetism, it's T squared over S to the fourth. Field intensity is T over S to the third. For magnetism, it's T squared over S to the fourth. Resistivity is T squared over S to the second. T squared over S squared. For inductance, magnetism, T to the third over S to the third. Electrical resistance, T squared over S to the third. And permeability for magnetism, T to the third over S to the fourth. Here then we have a solid foundation for a critical analysis of magnetic relations, one that is free from the dimensional inconsistencies that have plagued magnetism ever since systematic investigation of magnetic phenomena was begun. In the next chapter, we will apply the new understanding of magnetic fundamentals to an examination of magnetic quantities and units. And that is the end of chapter 19. Tomorrow we will start up with chapter 20, which is called Magnetic Quantities and Units. And so please tune in then to learn more about magnetic quantities and units and the reciprocal system of theory in general. Thanks for tuning in today. Have a great